We present our work on electroadhesive Auxetics as programmable layer jamming skins for formable crust shape displays. Shape displays are a class of tangible user interfaces that enable whole-hand haptic exploration of 3D surfaces. They are powerful tools for design and architecture, enabling tactile manipulation of CAD models, physical user interfaces that can adapt to individual users or tasks, and accessible 3D prototyping tools for blind or visually impaired makers. Conventional shape displays use an array of linear motors that move up and down to dynamically render a discretized 2.5D depth map. However, discretized approaches scale poorly to the smooth surfaces common in engineering and natural structures, and shape displays like those on the right with sufficient render resolution generally require thousands of individual parts and can cost thousands of dollars. Embedding actuation into the surface itself can allow a flexible substrate, commonly known in the literature as a formable crust, to continuously bend into the desired curvature, opening a new design space for shape rendering. Prior work has explored pneumatic and shape memory alloy arrays, but have generally required complicated and expensive fabrication or high power consumption in order to scale to large array sizes. Due to these scalability challenges for traditional elastomeric materials, we explore embedding actuation into auxetic substrates instead. Auxetics have a negative Poisson's ratio, allowing them to expand and conform to high curvature surfaces. Prior work, like on the right, has explored passive auxetic skins that are pre-cut for a single target shape, showing how dense, locally constrained cells like those indicated expand less when wrapped as a strain-limiting layer onto a pneumatic pouch. We propose that integrating layer jamming capabilities can allow a single auxetic pattern to programmatically produce a wide range of shapes. Jammed auxetic unit cells have limited expansion, creating high stiffness regions, while unjammed cells can expand freely. Programmatically locking different cells enables on-demand shape change. We implemented this actuation via electrostatic adhesion between stacked PCBs, as shown on the left. Electroadhesion is the attractive force between two metallized surfaces separated by a dielectric and held at a potential difference. It has high force density relative to its low mass and power consumption, and auxetic flexible PCBs serve as a scalable platform for migrating this planar actuation modality to a flexible form factor. First, we characterized an individual auxetic unit cell layer stack. We performed hysteresis tests on auxetic unit cells with and without electroadhesive layer jamming. The normal force on each unit cell from electroadhesion induces a frictional torque, preventing individual squares from rotating in place and thus increasing the axial stiffness. We measured the additional force required to stretch the 5% strain with electroadhesion versus when the voltage is 0, and compared experimental data with a solid mechanics model for 3 dielectric materials with relatively good performance. We proceeded with a dielectric PVDF HFP, whose high dielectric constant gave it high performance at voltages and currents safe for human interaction. We then fabricated a 5x5 auxetic unit cell array. Towards its functionality as a variable stiffness surface for a formable crust shape display, we tested whether locking local subsets of auxetic unit cells can affect the array's global axial and transverse stiffness. We axially offset two auxetic sheets by half a unit cell and clamped them to an Instron 5560 for a tensile test. The plots showed that rows can be locked programmatically to control axial stiffness in real time. At high strain, out-of-plane deformation causes layer jamming to fail, as shown. Unlike traditional uniaxial soft robotic applications, shape displays can make use of biaxial stiffness control to generate a more diverse range of shapes. As shown on the left, we varied the number of columns locked and measured the sheet's bending angle when given rotational freedom via ball bearings. The right compares experimental rotation angle to a model, showing good conformity at low strain but more bending than expected at high strain, likely due to out-of-plane deformation increasing frictional torsion. Next, we explored the application of electroadhesive auxetic skins for continuous formable crust shape displays. We mounted the 5x5 auxetic unit cell skins as a strain-limiting layer onto an inflatable low-density polyethylene pouch. The LDPE is locked at the edges between two laser-cut acrylic sheets, and when air is pumped into the pouch's interior cavity, the shape display balloons outwards into a uniform dome. We show a side view of how selectively locking different auxetic unit cells can change the sheet's axial and transverse stiffnesses, modulating the output shape's curvature. The auxetic skins achieve a 2.3x decrease in global curvature between the unlocked and fully locked cases, and they enable a 2x change in the output slope between the display's left and right sides for the 80% locked case. This enables the rendering of a broad range of shapes, as shown in the above video. While inflation speed was limited by our pump's airflow rate in this demo, we believe this forms a strong qualitative baseline for the actuator's performance and to motivate future work in continuous shape displays. We also recorded height maps using a Microsoft Kinect for more quantitative analysis, which is shown in the paper. In this work, we motivate the application of electroadhesion as a layer jamming actuation mechanism for auxetic sheets and demonstrate its usage as a programmable strain-limiting skin for a formable crust shape display. By using monolithic fabrication techniques like flexible PCB manufacturing and laser cutting, these actuators present a scalable, low-cost, low-power, and easy-to-assemble approach to integrating variable stiffness capabilities into flexible robotic systems. We envision future work will investigate integrating capacitive proprioceptive sensing into these PCBs and to explore more auxetic patterns to increase flexibility. Thank you very much for watching, and please feel free to reach out if you have any questions. Have a nice day.